Hello dear students, welcome you all. Well, in this lecture I am going to discuss about the next digital modulation technique, that is DPSK modulation. DPSK stands for Differential Phase Shift Keying. Right? So in the earlier lecture I have discussed about the binary phase shift keying modulation technique. Now this is the differential phase shift keying. So why this differential phase shift keying is required, why it was invented. So to answer this question we have to go back in BPSK. Right. In BPSK, we know very well the problem arises when we want to decode the BPSK signal or we want to demodulate the BPSK signal. To do demodulation or detection of BPSK signals, we require synchronous detection method or coherent detection method, we can say. This is the major drawback of this BPSK signal, right? Because we know very well that to do the coherent detection of the BPSK signal, we require the carrier wave of the same frequency, same phase, same amplitude that was used at the modulation end. When this signal was generated, the original signal was, original message signal was modulated and the BPSK signal was generated. So at that time, we definitely have used a carrier wave. Now, if we want to do the detection or demodulation of a BPSK signal, then we again require that wave. So it is done in two ways, either producing this carrier wave with the help of a local oscillator or either extracting it from the incoming BPSK signal. So this makes this entire process a very complex, right? And it is very difficult to design these circuits of generating the matching waves, right? So the complexity of the circuit is very high, and it becomes a major problem with BPSK signals, right? Another problem is the requirement of high bandwidth, right? But the main problem is coherent detection method, or we can say synchronous detection method of BPSK signals. Now, to do away with this problem, or to solve this problem, this DPSK modulation technique that stands for differential phase shift keying, it is invented. In detecting DPSK signals, coherent detection method is not required. There is no need to have a carrier wave of same phase or a frequency that was used at the time of modulation. These signal can be decoded or demodulated in a very easy way, right? We'll see at the end of this lecture, and I will come to the DPSK demodulation, right? So this is about the DPSK modulation. Now, how does it work? So in differential phase shift keying, right, the input bit stream is compared, every bit is compared with the previous bit, and according to that a new bit stream is generated, and then according to that new bit stream, new phase difference is induced in the high frequency carrier wave. So this is the way of working of this DPSK, right? What I said that the incoming bit stream, right, every bit of that bit stream is compared with the previous bit, right? And then according to that we generate a new bit stream, and according to that new bit stream we change the phase of a high frequency carrier wave. You can see here this entire process. Here what we have a incoming bit stream, that is input data, it is shown here. It is applied to a XNOR gate. The other input of XNOR gate is the 1-bit delay. What is 1-bit delay? The bit stream that is coming out of this XNOR gate, right? So I said you that we modify the incoming bit stream, right, by taking the consideration the previously generated output bit. So what we will do, we will take the XNOR action of incoming bit with the previously output bit, and then according to that we will have a new bit stream that will be modulated with the help of carrier, with the help of a product modulator, and we will get a DPSK signal. Right. So this is the main working, or the central idea of DPSK modulation. Now, before going into the entire DPSK modulation, first of all, I want to recall the truth table of XNOR gate. You can see here it is the circle symbol. Truth table, you can say it is for two inputs, 0 0 1, 1 0 0 0 1 0 and 1 1 1. So you can see we are getting output 1 only when both the inputs are same, right? Otherwise we are getting a 0 output. So we know very well the working of XNOR gate. So we have to actually remember this truth table because it is going to be used here, right? Now I am coming to the actual process that is done in a DPSK modulator. So you can see here this is the this circuit is drawn here, right? So in actual we have a you can see here logic circuit that is of XNOR gate. Then we have a delay circuit that delay this bit y 1 bit, right? Then bipolar NRZ, its task is to convert the bit stream into bipolar NRZ format, non-returning to 0 format, and then we are sending it to the product modulator, and this is the high frequency carrier wave A cos of omega ct. It is represented here, you can see here. Then after we will get the output, right? Now, in order to understand the working of this DPSK modulator, let's go to the table, right? Let this incoming bit stream is represented as B of t, right? And this delay, whatever delay we are getting here, it is represented as d of t minus 1. The output is represented as, and this output is represented as dt, right? You can see here in the table. So first of all, I want to draw the table. So then after the things will become very clear, right? Let we have the input bit stream as we can choose any bit stream. So I have taken 1 1 0 0 1 0. Right. Now what I require? This is the input bit stream, right? That is coming from here. 1 1 0 0 1 0. Now for the first bit that is coming, right, this one, what I require? I require a delay bit, right? Suppose the delay bit that we are using here, let it is 1, right? This one, dt. The originally, this the initial bit that was present here, that was 1. So that will be actually present here because we are starting from here. So dt minus 1 will be obviously what? 1. Right. Now what will be the to understand it in a better way, let's leave this column blank. So let's start from the next column. So then in that case, this will become, I am drawing it again. Bit stream was 1 1 0 0 1 0, and dt, the initial bit that I transmitted, that is 1, and then after we will get dt minus 1, right? So dt minus 1 is obviously 1, right? Now this bt and dt minus 1, now the things will become very clear, right? Initially I have one bit here, the bit that appear here is 1, and the output was also 1, so this is going to here, right, without any delay, because it is the only bit we are starting from here. Then we are going to perform the XNOR operation on 1 and 1. So 1 1 means, you can see here 1, so output is 1. Here I am going to get 1, right? Now that one is again, when I am delaying it by 1 bit, then again I will have 1 here. So then when I will have 1, again I will have 1, right? So then after again when I am going to this position, this bit, for this bit, again dt minus 1 is what? It is 1. So 1 0, it is a 0, right? You can see here XNOR of 1 0 is a 0, right? So in the same way you can then proceed to the next bit. Now this, for this bit, what is the output? dt minus 1, it is a 0. Previous bit is a 0, so 0 0 1. Now this bit is a 1, so it is going to act here 1 1 1, right? So this, in this way, this is then the next bit 1 1 0 0. So you can see now this truth table. This is the initial bit that I took as 1. Even you can take it as a 0. So this is the now required bit stream, that is 1 1 1 0 1 1 0. This is the generated bit stream, right? This is dt minus 1, right? 1 1 1 0 and 1 1, right? And this is the original bit stream 1 1 0 0 1 0, right? So now I have a new bit stream that is represented by this, right? And this bit stream is generated by taking into the comparison of the 1 bit delay, taking the XNOR operation of the present bit and the previous bit, right? So now I have this bit stream. Now I'm going to generate this bit stream here, dt, right? You can see here in this format here. So now I'm going to represent this dt here in the form of wave. It is 1 1 1 0 1 1 0. So I can represent it here. Bun, right? 0, right? 1 1 0, then again 1 1 0 1, then again 1, then 0. You can see 1 1, then 0, 1 1 1 0 1 1 0. So this is again then 0, right? So I can write here corresponding to it. It is 1 1 1 1 1 0, then 1 1 0. So this is what? This is dt. Now it is a new bit stream. You can see from here, this is different and this is different. Now this bit stream is given to the bipolar NRZ format. So what it will do? It will convert it simply into a bipolar format. 1 2 3 4 5 6 7. So you can have this format, bipolar NRZ format, in this way: 1 1 1, right? Then 0, then after you will have this one, then again 1 1, then again it is a 0. You can see here now it is bipolar NRZ format of this signal. It is 1 1 1 0 1 1 0. So I have told you what is bipolar NRZ format in the earlier lecture also. So now this is mixed with the high frequency carrier wave A cos of omega ct, and this product modulator will now change the phase of this high frequency carrier wave in accordance with this signal, and according to that we will get the whatever signal we will get, that can be represented as plus minus a cos of omega c t, right? Now I am coming to once again coming to the truth table. You can see here. Now you can see this truth table. It is clear from this truth table that the new bit stream dt is created in such a way that when there is no transition in the incoming bit stream with respect to the previously transmitted bit, then the bit generated is 1. You can see here no transition 1, right? But there is transition now. The previously transmitted bit was 1 and the incoming bit is 0. So it is represented as now 0. So then again same thing, no transition 1, no transition 1, transition 0. So I can say that in this DPSK modulation, the bit stream is modified in such a way that when there is no transition between the incoming bit stream and the previously generated bit, then the new bit stream generated is 1. But if there is transition of the bits with respect to the previously transmitted bit, you can see here there is a transition 0 to 1 or from 0 to 1, then the new bit that is created is 0. So according to this, now we have this bit stream. Now according to this bit stream, we are going to change the phase of a high frequency carrier wave, and the phase is changed in such a way that if the bit is 1, there is no phase change, right? 0 degree phase change is there, but if the bit is 0, then the phase change is pi or 180 degree. You can see pi, right? Now you can see here in this table that a phase change of pi will occur only when there is a transition between the two successive bits. You can see here 1 to 0, pi phase change. But when the bits are same, no change in phase, right? No change. But again, when the bit is changed, then there is a change of phase. So this is the way of working of this DPSK modulation and how the phase is changed. So according to it, we will have a waveform of this DPSK, signal. So this is the phase 0 0 0, then pi, then 0 0, then again pi, right? So I can draw this waveform here. I will have this original waveform as it is 0 0 0, no change, right? Because I have for the 3 bits no change of phase, but then I have a phase change of 180 degree, right? 180 degree means I will change the phase, right? But then after no change for the next 2 bits, right? But then again there is a change of phase of 180 degree. So you can see here the phase change is there and there. It is 1 1 1 0, then 1 1 0. You can see here 1 1 1 0 1 1 0. So this is the resultant DPSK signal, and in this signal there is phase change only when there is a transition between the previous bit and the incoming bit 1 to 0, or it can be 0 to 1, then only there is a phase change of 180 degree, otherwise there is no phase change. So this is the DPSK modulated signal, right? Now the next step is and the important thing is how to extract this signal at the demodulator, because it was invented to remove the problem of coherent detection. So now I am going to explain how this signal is detected, right? So for demodulation, you can see here the diagram, the process that is followed at the demodulator or the detection center. This is the DPSK signal that is coming from here. it is going to be mixed with the balanced modulator. This circuit is basically a multiplier, right? Balanced modulator is a multiplier. I can write here. And this is one with delay again, and then low pass filter, and then shaper means it is a decision making. I can say decision making circuit. Decision making circuit, right? I will explain all of them one by one. Now, let's see the different possibilities, right? Let the incoming signal, we can see here, it is either plus a cos of vega ct or minus a cos of vega ct, right? So, when we have, suppose the incoming signal is plus a cos of vega ct, right? This is one possibility. The incoming signal is plus a cos of vega ct. Let the previous bit, that was also plus a cos of vega ct. Then when they will go there, the product modulator will do the multiplying of these two signals, and according to that we will get some positive. I can say it will be a square cos square vega ct. I can say that, right? And then after it will be passed through a low pass filter. The output of the low pass filter will be obviously a square divided by 2, kind of that, right? And the other harmonics will be removed from here, right? Because when I will expand this term, it can be expanded 2 cos square theta, so 1 plus cos 2 theta, in that way. And then when we pass this to the low pass filter, the undesirable frequencies are removed. We are left with only plus a square divided by 2, and then this plus a square by 2 is passed through a decision making circuit. Now the reference level of this decision making circuit is I can say threshold level. Let it is 0 volt. So this is going to compare or take a decision whether the incoming signal is greater than this or less than this. If it is greater than this, obviously it is positive, it is going to create a 1 bit, right? It is going to generate bit 1. But if the incoming signal is less than 0 volt, it will generate the bit 0. In this way, decision making circuit will work, right? Now the second possibility here is it is minus a cos of vega ct, and here it is also minus a cos of vega ct. This possibility is also there. In that case, again I will have positive, and the same thing is there. But the other possibilities, here it is positive and here it is negative. In that case, when the product will be there, the product will be negative, and I will get negative a square divided by 2. So then after the decision of the decision making circuit will be different. So according in this way, we are going to generate the bit stream, right, from the incoming bit stream. So this is the way of working of this DPSK demodulator. The thing will become very clear when I will come to the truth table, or I can say the tabular diagram of the incoming bit stream and the original the recovered bit, right? So BT is what? The original bit stream that is coming from that was used here, right, for the encoding. It was 110010. It is 110010. And what is DT? DT is 111011. 111010, right? What was the phase of this DT? We have seen it is 0 0 0 pi 0 0 pi, right? So you can see here. Now what is dt minus 1? Dt minus 1 is this bit delayed by 1 bit duration. I think this should be started from here, because 1 was the the bit that was started in the beginning. We have taken 1 at that time, so it should be used here. 1 1 1, then here it should be 0, then 1 1 0. 1 1 1 0 1 1 and 0, right? So it was a dt 1 1 1 0 1 1 0, right? Now what is dt minus 1? We will start it from here because this was the starting bit, right? So it is now, when it is delayed by 1 bit, it will start from here. 1 1 1 0 1 1 1 1 1 0 1 1 and then 0, right? Now as far as the phase here it is concerned, phase of dt, so it was now once again I have to change it, this table. The phase was corresponding to 1, it is 0 0 0, it is pi 0 0 and it is a pi, right? So this is dt minus 1, right? 1 1 1 0 1 1 0. Now what is the phase of this dt minus 1? We have seen it is 0 0 0 pi 0 0 and pi, right? We have seen how this phase is generated, right? So now let's see at the phase, because here I told you, when these two waves or bits are in the same phase, whether they are negative negative or positive positive, the output bit will be 1. But when they are out of phase, the output bit will be 0, because at that time here we will get minus a square divided by 2, and that is less than reference voltage, and so according to it the decision will be 0, right? So now let's see here. Here it is the phase of the original bit and the phase of this same phase, right? So the bit generated is 1. So here same phase, right? This one bit generated is 1. Now here it is the phase difference, 180 degree out of phase, bit generated is 0. Here again there is a phase difference, so bit generated is 0. It is same phase, bit generated is 1. It is phase difference of 180 degree, so bit generated is 0, right? So you can see now what is the working of this DPSK demodulator. Now you can see here the recovered bit stream, very very important. It is 1 1 0 0. So original bit stream 1 1 0 0 1 0 1 0. So this is the way you can see here, right? So this is the way of recovering of this original bit stream that was used here, right? So in DPSK demodulation, it is very clear that there is no need of using a coherent detection method, or we don't require a cos of vega c t, right? That was the carrier wave of high frequency used at the time of modulation. So there is no need of it, right? This incoming bit stream is recovered in such a way that we can do it without taking into account of high frequency carrier wave. So this is the way of recovering this information. You can see from this table how we done it. We took the original bit stream here, right? Then dt, what was dt? So for dt we have to see here. Then the phase of dt, right? Then delay, we delayed the dt by 1 bit. So delayed means we are now starting from here. Then phase of this, then comparison of the phase of these two, right? This one dt and dt minus 1, right? And then the decision. So it is coming from here dt, and it is here dt minus 1, right? This is the product, and then product will be plus a square cos square omega ct or minus a square cos square omega ct, it is passed through low pass filter, we will get either plus or minus a square divided by 2. It is passed through the then decision making circuit, and then we get the corresponding bit stream, whatever it is, 110010, whatever it is, that will be recovered, right? So this is the working of a DPSK demodulator, right? Now as far as advantages disadvantages are concerned, so I told you in the beginning that the sole purpose of DPSK modulation is to remove the requirement of coherent detection at the demodulator, and it has an advantage of reducing the required bandwidth also, right? So this is all about the DPSK modulation technique, right? So thank you very much.